Welcome viewers to the second segment of the sixth lecture for the online series of lectures for the course of Algebraic Topology 1. Towards the end of the previous segment, we listed two properties of general n simplex. Now we will discuss the rest of the properties of a given n simplex. A subset A of R to the n is said to be convex if for each pair of points x, y in A, the line segment joining them lies in A. Okay, so that if intuitively, if we have a set which looks like this is not a convex set in R2 because this point and this point, if we pick up these 2 points and inside this region, then the line joining these 2 points in R2 does not entirely belong to this region. Therefore, it's not a convex set. A convex set is something like a polygon or something like a ball. Okay, this is a convex set. If I choose any 2 points from this ball, that will entirely be contained inside the ball. Okay, so that's the concept of a convex set in R to the n. Now our third property for an n simplex is as follows. This n simplex sigma is a compact we know the topological property of compactness from our study in points topology, right? And this n simplex sigma is a compact convex set in Rtdn. Okay, it is closed, it is bounded, and it is also convex, which this convex set is the intersection of all convex sets in Rtdn containing this n plus 1 points, containing A0, A1 all the way up to AN. Okay, which means that these are n tuples, right? Which means that these are n plus 1 points in this Euclidean space, and there are convex sets containing these n plus 1 points. We need the smallest convex set containing these n plus 1 points, and that smallest convex set is nothing but this n simplex. Okay, this is what this third property says. Okay, all right. Now the fourth property states that given simplex sigma there is one and only one geometrically independent set set of points spanning sigma. Okay. So while defining this n simplex sigma, we used n plus 1 points. And to start with, we need these n plus 1 geometrically independent points, right? And this fourth property states that there can be more than one set of geometrically independent points that to span this n simplex sigma. Okay, there can be more than one set. Okay, there is exactly one set of geometrically independent points that span this n simplex sigma. Okay, good. So the points A0, A1 all the way up to AN that span this n simplex sigma are called the vertices of sigma. Okay, so associated with an n simplex sigma, there are n plus 1 vertices. Okay, the number n here, okay, the number n is called the dimension of the simplex. The number n is called the dimension of the simplex sigma. Any simplex spanned by a subset of these points of vertices. So if you pick up any subset of these endpoints, geometrically independent points in R to the n, then those points, that subset of these endpoints spans another simplex. Okay, and that simplex, any simplex spanned by a subset of this set, is called a phase. Of sigma. The phase spanned by these endpoints A1, A2 all the way up to AN is called the phase opposite to A0. Okay, so it's time to give you an example first. Okay, so in R3 one can have 4 points to form a tetrahedron. Okay, so let me draw the picture of a tetrahedron. Something like this. This is the picture of a tetrahedron, right? And let's call the 3 points of this triangle to be A1, A2, A3, and this one to be A0. Okay, so so there are 4 points A0, A1, A2, and A3 that span the 3 simplex sigma. Okay, so this is sigma, and now see that one can have this triangle A1, A2, A3, which is this shaded region, which is the face opposite to A0. Okay, now consider this face. Okay, face, this is face opposite to A0. Now we can take this face in the picture, which is the 2 simplex formed by A0, A1 and A2. This is face opposite to A3, right? To A3, okay? And this is a 2 simplex. This is also a 2 simplex, right? Which is a face which are faces of this 3 simplex sigma, right? Denoted by 3 simplex sigmas spanned by these 4 points, 4 geometrically independent points in R3. Okay, but this A2, A3, okay, A2, A3 is this line, right? This is also a face of sigma, right? Because this is a proper subset of the set consisting of these 4 geometrically independent points, right? So this is sometimes it's called proper face, right? Which arises from a proper subset of the given set of vertices of the n simplex. Okay, so this was a small example illustrating how we get faces opposite to vertices. Now there are more terminologies, okay, related to the properties of an n simplex. The faces of sigma, the faces of sigma are different from sigma which result in by taking proper subsets of the set of vertices, right? The faces of sigma different from sigma itself are called proper faces of sigma. Okay, so we had a look at two types of proper faces of sigma in the case of a three simplex, which is a uh, tetrahedron, right? Tetrahedron in R3. Okay, proper faces of sigma. The union of the proper faces of sigma, the union of the proper faces of sigma is called the boundary of sigma, okay, and is denoted by BD sigma. Okay, so if we draw the tetrahedron again, which look like this, A0, A1, A2, A3. Okay, now this is one proper face, this is also a proper face, so uh, there are four proper faces which are two simplices or triangles, right? So and then this proper face, which is spanned by A1, A3 and A0. Okay, so in this case there are uh, two simplices which are like A0, A1, A2 is one proper phase, then one has A1, A3, A2, then one has A0, A2, A3, and finally one has A0, A1, and A3. There are four proper faces which are two simplices, right? And then one has A0, A1, which is uh, uh, one simplex, which is also a proper phase of the three simplex we are dealing with. Okay, so A0, A1, then one has A1, A2, then one has A0, A2. Okay, then we have A1, A3, this is a new one. Then one has this guy, right? A2, A3, A2, A3. Okay, then one has A0, A3, which is also a new one, right? A0, A3. And so there are 1, 2, 3, 4, 5, 6. I think there are 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. So there are 6 one simplices. And how many vertices are there? There are 4 only, right? 4 zero simplices. Okay, so the union of these, so these are the 6 simplices, and the the 4 zero simplices are A0, A1, A2, and A3. Okay? The union of all these proper faces constitute the boundary of these 3 simplex sigma. Okay, so the boundary of sigma is the union of all these proper faces of this 3 simplex. Okay, good. Now the interior. So the interior is the 3-dimensional region enclosed by this tetrahedron. Okay, that's an open set of Rtdn. Well, in this case, R3. Okay, so the interior of sigma is defined by the equation interior of sigma is equal to sigma set minus the boundary of sigma, okay, which we number as equation number 8. The here interior sigma is the region inside this inside this tetrahedron. The set interior of sigma is sometimes referred to as an open simplex. Okay, so if you want to look at the story of a 2 simplex, which is the triangular region inside, interior to these 3 lines joining the 3 vertices A1, A2, and A0, then the interior of these 2 simplex is this open triangular region, okay, without the boundary. It does not include either the vertices or the 1 simplices, which are the proper faces of these 2 simplex. Okay, all right, so the boundary of this 2 simplex is the union of these 3 1 simplices and 3 vertices, or the 3 zero simplices. So that those are the proper faces of these 2 simplex, and you take the union of these proper faces that constitute the boundary of these 2 simplex. If you extract out this boundary of the 2 simplex, what you get is an open 2 simplex, okay, which is the open triangular region inside this inside these 3 lines joining the vertices. Okay, so good. Now the 5th property, tells us that interior of the n simplex sigma is convex and is open in the plane P. Its closure, so it's open, but its closure, and its closure is the n simplex itself. Okay, so you take the limit points you know, and you know, and the union of all the limit points is the n simplex itself. Furthermore, interior of sigma equals the union of all open line segments, all open line segments. It's important that they have to be open line segments joining A0 to the points of interior of the simplex S, where S is the phase, is the proper phase, is the phase opposite, is the phase of sigma, the n simplex sigma that we are studying, opposite to A0. Okay. All right, so let's see how it looks in the context of the two simplex, which is the triangular region. Okay, so um, so this is this is the boundary. Okay, let me redraw it. Okay, so uh, let me draw the boundary by dotted lines. So this is the boundary of the two simplex. Okay, two simplex. Now this is A1, this vertex is A1, this vertex is A2, and this vertex is A0. So we are taking all open line segments. Okay. So the interior of S, the face opposite to A0, is this open line. Okay, the boundary of this one simplex is so um, so the boundary of this one simplex is precisely the union of these two vertices A1 and A2. So you exclude these 2 points from the one simplex that we have drawn here, and what you get is the interior of the one simplex S, okay, in the context of these 2 simplex. Okay, and now you've got to join A0 to the points lying in the interior of this simplex, one simplex S, and these open line segments. Okay, these open line segments, you have these open line segments, and you take the union of all these open line segments, and that is precisely the interior of the two simplex sigma. Okay, so this is how we see the fifth property in the context of the two simplex, which is the triangular region, formed, spanned by these 3 geometrically independent points A0, A1, and A2. Okay, so now we need to list a few known facts about R to the n, the Euclidean space. Okay, so some known facts about R to the n. So whenever we have an element or a point of this Euclidean space of dimension n that is represented by an n tuple, right? x1, x2, all the way up to xn, right? So a vector is, this is a vector, this n tuple is a vector, of course, right? And or if you want to think about it, if you want to consider it as a topological space, and a point in this topological space is represented by an n tuple. The norm of X, it's a norm vector space, or if you want to call it a topological space, um, where the topology is induced by the norm. You can also say that the norm of X is defined by this expression. You take the sum of all the squares of the components, and then take the square root. So this is what we call equation number 9. The unit n minus 1 ball Bn is the it's not an n minus 1 ball, this is an n ball. It's called an n ball and denoted by b to the n. The unit n ball is the set of all points for which one has norm of X, all points X for which norm of X is less than or equal to n. Okay, so we can think about it in 3 dimensions. Okay, this is x-axis, this is y-axis, this is z-axis, and one can draw a 3 ball here. Okay, which is the interior of the 2 sphere, right? Which looks like this. So this is B3. This is B3. So it contains the boundary as well. Okay, everything inside the ball, including the boundary, is called B3, or the 3 ball. Okay. Okay. Now the unit sphere s to the n minus 1 is the set of points for which the norm is exactly 1. Set of points x for which the norm of x is equal to 1. It constitutes the surface of this 3 ball, which is a 2-dimensional surface, right? With these definitions, B0, so this was the example of B3. So what about B0? B0 is just a point, is a 1-point space. Okay, B1 equals the interval -1 to +1, okay, this closed interval. And so S0 is going to be the boundary of this one ball, right? And the boundary of this one ball is the union of these 2 points, -1 and +1, the endpoints. And S0 is the 2-point space, right? 2-point space, which is the boundary of this uh, uh, closed interval, right, from -1 to +1, which is the union of these two endpoints. Okay, the two ball B2 is the unit disk in R2, unit disk in R2 is centered at the origin. If you want to picture it, it looks like this. This is x-axis, this is y-axis. We have this R2 thing, the rectangular coordinate system, and then we can draw a unit disk here, which is this region, right? This this ball, this two ball is drawn around the center 0, 0. Okay, so this is two ball. And what is S1? S1 is the boundary of this two disk, which is this circle, S1. This boundary is S1. S1 is the unit circle. Okay, all right. All right, now we can talk about the sixth property of an n-simplex, which is that there is a homeomorphism of the n-simplex n-simplex sigma with the unit ball Bn. Ball Bn. Sorry, this is capital N simplex. Okay, that carries the boundary of sigma. That carries the boundary BD sigma onto the boundary of this n ball, which is n-1 sphere, onto the unit sphere s to the n-1. Okay. Okay, so if you want to look at this property in the context of a two-simplex, right? So think about a two-simplex, which is this triangular region. Okay, this is sigma. Okay, this is this triangular region, and this guy is homeomorphic. So if I try to draw the unit ball here, then it's homeomorphic to this unit ball. Okay, B2, where this boundary is carried. So under this homeomorphism, this boundary of this triangular region is going to be carried to this boundary of the two ball, which is the unit circle S1. Okay, and the interior of this uh, triangular region, which is interior of sigma, is going to be carried to the interior of these two disks. Okay, under this homeomorphism. All right, that's enough. So we listed 6 properties without any proof, but we gave plenty of examples so that you have the intuitive concept of these 6 properties. It will be left, as exercises for you to prove some of them, some of the properties of an n simplex. Okay, so now it's time to define a simplicial complex. Simplicial complex. So in order to differentiate it from an abstract simplicial complex, we can call it a geometrical simplicial complex. So whenever I say simplicial complex, I will mean geometrical simplicial complex. And when I mean abstract simplicial complex, I will call it abstract simplicial complex instead of just calling it simplicial complex. Okay. Geometrical simplicial complex. Definition. A simplicial complex K in Rtdn is a collection of simplices in Rtdn such that the following hold. Okay, you just can take an arbitrary collection of simplices in Rtdn. It will not work. They have to the collection has to fulfill a couple of properties. Okay, so here the things that need to be satisfied to so that we can call the collection of these simplices a simplicial complex. The first property, every phase of a simplex sigma of this complex K, of this collection K, is in K. Okay, it's important. So it means that we cannot have something like this. Say we have this triangular region, meaning that this region bounded by these two faces, right? But we don't have this remaining face of these two simplex. Okay, this vertex is present, this vertex is present, this vertex is present, but this face is not present. And again we have, say, another one simplex here. Say we can also have this another two simplex here. Okay, and the one simplex here like this. We cannot call it a simplicial complex because for this simplex the face is not included, so property 1 fails. Right, so this was property 1. The second property is that the intersection of any two simplices sigma and omega of the collection K is a phase of each of them. Okay, all right. So these two properties need to be fulfilled. So let us have a bunch of examples. Say a two simplex. So the collection is just a two simplex. We call it K1. K1 is a simplex. K1 is a simplex. So K1 is a simplicial complex. It consists of only one simplex. Okay. Now this is an example of a simplicial complex which has two simplices. Okay, and the two simplices intersect at a phase, and that intersection, in other words, that phase is the phase of both the simplices, both the two simplices, meaning that this is the intersection of these two simplices, and this is a phase of this simplex, and this is also a phase of this simplex. So this is a valid simplicial complex. Okay, now we can have a collection like this. Okay, this is one simplex and this is another simplex, but together they don't form a simplicial complex. Why? Because they intersect at these line segment, and this line segment is not a phase of any of these two simplices. Okay, so this is not a simplicial complex. Now we have two simplices, okay, which intersect at a point, and this point is a phase of this two simplex, and this point is also a phase of these two simplex, and hence both the properties are fulfilled and it is a valid simplicial complex. Okay, now I state an important lemma without proving it. Lemma 1, a collection, so it's rephrasing one of these two properties. Okay, I'm just rephrasing the second property to be, to be more precise. The first property stays as it is, but the second property is rephrased. A collection K of simplices is a simplicial complex if and only if the following hold. Nice result to check if a union of complex simplices actually forms a simplicial complex or not. 1. Every phase of a simplex of K is in K. This is exactly the same as as we had in the definition of simplicial complex. And 2 prime, we call it 2 prime because it's equivalent to 2, so 2 and 1 maybe, I did not go over the proof. The interested readers are encouraged to go over the proof. Every pair of distinct simplices, every pair of distinct simplices of K have disjoint interiors. Every pair of distinct simplices of K have disjoint interiors. Okay, which means that the interiors of the simplices cannot, intersect each other. So, which means that collection like this is not possible. This is not a simplicial complex because they don't have disjoint interiors. This is one simplex and this is the other simplex, and they have a non-empty overlap of the interiors, which is not possible according to 2 prime. Okay, the proof is omitted. Now we have a definition of subcomplex. We have sub things in mathematics, like we have a vector space, we have a vector subspace associated with a vector space. Then we have the structure of group in abstract algebra, and we have the subcomponent of this group, which is a subgroup. Now we have a complex, simplicial complex, and then we can form a simplicial subcomplex C. What's the definition is of a simplicial subcomplex? If L is a subcollection of K, where K is a simplicial complex, okay? L is a subcollection of K containing all faces of its elements. Faces of its elements. Then L is a simplicial complex by its own right. Complex L is a simplicial complex in its own right. It is called a subcomplex of K, subcomplex of the simplicial complex K. Okay, one subcomplex subcomplex of K is the collection of all its simplices, collection of all its simplices of dimension at most b. Okay, it is called P skeleton. It has a name. It's called P skeleton of K, and is denoted by KP. Okay, the points of the subcomplex K0 are called the vertices of K, called the vertices of K. Okay. Okay, so let's take a simplicial complex, something like this, a very simple simplicial complex. So two simplices intersecting at one vertex. This is a simplicial complex. Let's call these vertices A0, A1, A2, A3, and A4. So now it is a simplicial complex, we know from the definition of a simplicial complex. So now I ask you to find the one skeleton of this complex, right, which will be a subcomplex according to this definition. So according to this definition, it will include is a collection of all simplices whose of dimension at most 1. Okay, so it should include all one simplices that we have in this complex, like it is a collection of, you know, A0, A1, A1, A2, A0, A2, and A2, A4, A4, A3, A2, A3. Okay, not only that, we have to include the vertices as well, because these are just the one simplices, but we taking the simplices of dimension at most p, at most 1, which means that we have to include k zeros as well, right? So which are A0, A1, A2, A3, and A4. So this is a representation. This is a representation of the subcomplex K1, or one skeleton of this complex K. Okay. And the zero skeleton of this complex K is just a collection of, is just a union of this 5 singleton sets. Right? Okay, good. Now, so far we have talked about, simplicial complexes, but we did not give any topology on this complex. Now we'll study how we will study the possible topologies we can put on the structure of complex. Okay. Okay, let's get started with the definition. But before we do that, I think I'll take a break and get back to you with the definition of possible topologies that one can put on these simplicial complexes. Okay, thank you for attending this second segment.